Okay, let's start. There was a problem about the pigeonhole principle that a function from a finite set to itself is injective if and only if surjective. So here is a proof. Yeah. So injective implies surjective. We did that already, but we need it also for the reverse part. So I have written the proof down. Yeah, hopefully you will take it down. And for surjective implies injective, so I am not discussing the 1 implies 2 part. For 2 implies 1, if you have a surjective function, then from the pre-image of every element in the codomain, you can always choose one element which maps to it. Yeah, that's the definition of pre-image, and this such a choice defines a function. Yeah, you are making finitely many choices, so you just choose finitely many elements. And therefore there will be a function g such that f of g of y is equal to y for every y. In other words, fg is equal to identity. Now whenever such a thing happens, then g is injective. Yeah, this part is injective and this part is surjective. Right, so we have seen that. So g is injective, f is surjective. So in particular now g is injective, so by 1 implies 2 applied to g, g is also surjective. So g is injective as well as surjective, so it is bijective. And now because g is bijective, f has to be bijective. So that's the argument. Understood? What should I repeat? What part? From the start itself. Okay. So if f is surjective, then we can choose one element for so for every y in A, we can choose one x such that fx is equal to y. So we'll say that x is mapping to y. Y is mapping to x, and this defines the function g. And that g satisfies fg is equal to 1, fg is equal to identity, and therefore g is injective, f is surjective. Yeah, this you can easily prove. So in particular, since g is injective by 1 implies 2, which is written here, we know that g is surjective. So g is injective as well as surjective in particular, so bijective, and therefore since g is bijective, f also has to be bijective. If g is bijective, then you can simply multiply both sides by g inverse. Yeah, so fg g inverse is equal to g inverse, which means f is equal to g inverse. So inverse of a bijective function is bijective. So done. Right. So in particular, f is injective. That's what we needed.
How did you prove that g is surjective?
How did you? G is surjective because of this identity. This was one of the problems I wrote on the board. Right. So whenever composition of two functions is a bijection, what can happen? One function can embed into a larger set, and then from that larger set again we can get down to a smaller set. That's the only possibility. Try to prove this. Yeah, that's an exercise. So we have seen unions. Yes, unions of two sets, unions of a family of sets, arbitrary unions. Yeah, we have seen all those things. However, there is also one more operation which is not really a set per se, but bijection class of sets, and that is called disjoint union. So if you have two sets A and B, how do you take their disjoint union? If A and B are sets such that A intersection B is non-empty, then there are different notations. So A square bracket B or A, this notation B, yeah, denotes their disjoint union and is defined as the set and is defined to be the set. So if A and B contain common elements, then we try to separate them into two bijective classes by doing this. So A cross singleton 0 union B cross singleton 1. Okay, so what we did, something very simple. We took its cross product with two different sets. Singleton 0 and singleton 1 are two different sets, and respectively, I mean A cross singleton 0, B cross singleton 1, so that even if A and B have some intersection, A cross singleton 0 and B cross singleton 1 do not have any intersection, and therefore their union will be their disjoint union automatically. Yeah, so here can you observe that from A to A cross 0, yeah, so the map in this direction, which is defined by little a mapping to little a comma 0 and well a comma 0 mapping to A, this is, these two are bijections clearly, right? So I am just going to write these symbols, and therefore we are not really changing the set up to bijection. So therefore disjoint union is what you expect. I mean, why is disjoint union interesting? Because if you want to sum their cardinalities, then what will happen? Cardinality of the disjoint union will be precisely the sum of the cardinalities, individual cardinalities. Whereas cardinality of the union need not be. Yeah, it satisfies inclusion exclusion principle. Okay, so this particular thing is required for our purposes, disjoint union, and our main result about two sets having same cardinality is the Cantor-Schroder-Bernstein theorem. So let us write it down. So for sets A and B, if F from A to B and G from B to A are injective functions, then there exists a bijective function H from A to B. So think of it like this. Yeah, if there exists an injective function from A to B, then size of A is less equal size of B, and also size of B is less equal size of A, then actually their sizes should be equal. Yeah, so that's what we are trying to say. However, constructing this function H is not particularly easy. Yeah, can you share some ideas that you might have about this? Can you think of a way to prove this statement? Can we define this H to be F?
No, we didn't say A and B are like finite.
Right. So we cannot say that either. So F is not the answer. But sometimes F and sometimes G inverse. So G inverse is not really a function, but G inverse is a function from image of So we have, so I'm not going to write the proof here, I will write proof on the next slide, but for now, so there are two more injective functions. First one is G inverse, which is from G of B to B. This is a bijection, in fact. Yeah, G inverse is a bijection from image of G to itself. And F inverse is also a function from f of A to A. So now we have lot of data. So let us try to picture this. Oh, by the way, yes, why are there three different names? Yeah, in this, because Cantor gave the idea, Schroder wrote a proof which was flawed, and Bernstein corrected the proof, so all three names are present. And this is a very important result in mathematics, so it's named after all three mathematicians. Some people call it Schroder-Bernstein, some people don't want to give the credit to Schroder because Schroder proved it wrong. Yeah, so some people just call it Cantor and Bernstein theorem, but yeah, let's give credit to all those great minds. So A and B, yeah. So the image of A is sitting somewhere here. Yeah, this is our f of A. And the image of G is sitting here. So what is the idea? Do you want to share some thoughts? You have four functions which are injective.
So it's like B lies inside, B is injective with G of B.
Right, B is in bijection with G of B, yes.
So like उन दोनों का that
English.
So that will be equal number of elements. And A is in bijection with f of A. So the bijection, so the number of elements in both of them will also be same. So
how do we know that? That's precisely what we are trying to prove. You are telling me that size of G of B is less equal size of A, and size of A is less equal size of f of A, is equal to size of f of A, and size of f of A is less equal size of B, and therefore by sandwich essentially they are the same, and that is precisely the statement of the theorem. We still haven't proved that. Yes.
Basically, I was saying like if we are mapping one to one from A to B, then in set B, set A should be a subset of set A should have cardinality less than set B.
Don't think about cardinalities yet, yeah, because we haven't specified what cardinalities are. But again, I think your idea was around same lines. Yes.
There is an infinite descent here. Like if you map A to f of A, you map using G f of A to some subset of G of B.
Correct.
Keep repeating the process.
There is an infinite descent. Correct. Yeah, we will use that. Yes. Infinite descent, or something else.
So from G of B to like we can go to f of A and then like.
So where exactly should we use this infinite descent? So his idea is that, okay, so from A we can go to f of A, from f of A we can come back to a subset of G of B, from subset of G of B you can again go to subset of f of A, and that way we will continue with the process. Yeah, which is correct. But then does it make a decision, does this procedure make a decision for all elements of A? The idea is correct, you understand? Yeah, we keep doing this, we keep making it smaller and smaller, apparently smaller, but still they are in bijection, right? So let us use that idea, let us formalize that idea properly. So I always write this particular symbol, this arrow symbol, to denote proof. Okay. So first statement, and for this precise reason I wrote down the definition of disjoint union. So without loss of generality, assume that A and B are disjoint. Okay, we don't want any trouble afterwards. If they are not disjoint, we'll replace them with A cross singleton 0, B cross singleton 1. Yeah, nothing will change. The functions will still remain injective. Yeah. Okay, so now for A in A, consider the sequence. Just a moment. आपको बोला था फ्राइडे को आने के लिए, फ्राइडे को कोई नहीं आया, बाकी दिन सब आते हैं. फ्राइडे को डेफिनेटली आना है. राइट. सो फॉर ईच A in A, consider this sequence. Consider the sequence A. Then what can I apply to A? A is in A. F. Okay. F of A. What can I apply to F of A? G. So G of F of A. Then next element, F of G of F of A. I have to make sure I am closing equal number of brackets, and right. So this is the way this sequence will proceed. However, why should we stop here? Maybe the sequence will also continue backwards. If A itself is in the image of G, then I can also consider G inverse A. Then if G inverse A is in the image of F, then we can consider F inverse of G inverse of A, and so on. So this is potentially doubly infinite sequence. On both sides we are doing this. Okay. So there are three possibilities. For such a sequence. First one, well, the sequence is doubly infinite. So first notice that above it's always going to be infinite, correct? A, Fa, GFA, FGFA, and you can always keep applying this. Maybe the elements will repeat, yeah, but that doesn't matter. The sequence will continue, right? Whereas backwards, whether it continues or not, that's a question. So there are three possibilities. The sequence is infinite. On both sides. Then the sequence ends in an element of A. So such a sequence will call A stopper. So for example, if the A, little a that we started with, it doesn't belong to the image of G, then our sequence will stop here, right? Over here. These two will not be there, right? And third one, the sequence ends in an element of B, and that is a B stopper sequence. See, it can obviously happen that we have one element of A, so A maps to F of A and G of F of A is equal to A. Yeah, it's a perfect cycle. So we keep repeating and repeating and repeating, doesn't matter. That also falls under 1. Right? But there are these two different types of sequences, that the sequence ends in an element of A or sequence ends in an element of B. Now we have to make different choices, and this will be a piecewise choice for the function. But before we do that, first observe that every element of A lies in exactly one of these sequences. Correct? How? There is no other choice left. What does that mean?
It has to be either infinite or end in A or B.
No, we are not talking about whether it is infinite or A stopper or B stopper. That's not the point.
We start with A.
We start with?
Like we are starting the sequence with A.
We are starting the sequence with A, but maybe at the next step our A is this element. Yeah, I mean this could be A prime. I'm claiming that not only like two elements of A, but sorry, every element of A, but in fact every element of A union B, A disjoint union B, lies in exactly one of these sequences. Can you see that? If there are, so let me write down the formal statement. Each element of A disjoint union B lies in exactly one such sequence. Yeah, which means these sequences actually define an equivalence relation. This is a partition of A union B. Okay, when we are talking about equivalence relations, let's first ask the question, is this relation reflexive? Can A and A belong to the same sequence? Yes? A and A will lie in exactly the same spot. Fine. If A and B lie in the same sequence, do B and A also lie in the same sequence? Yes? So suppose, let me use a different color. Suppose this is my A and this is my B. Yeah, I mean it doesn't have to be from A and B respectively, capital A and capital B, but these are two elements. So we know that these two sequences lie in the, these two elements lie in the same sequence. So I can obtain this, I'm just calling it C0 and C1. I can obtain C1 from C0 by a sequence of F's and G's or F inverse and G inverse. But since F and G are injective, or F inverse and G inverse, whenever we can apply them, they are also injective, I can also come back from C1 to C0. Yeah, what is C0 in terms of C1? F inverse of G inverse of F inverse of C1. Right? So therefore, by injectivity of F, G and the restricted functions F inverse and G inverse, this is an equivalence relation. Since F, G and appropriately defined, this appropriately defined simply refers to this thing, yeah, that F inverse and G inverse are functions from GB and FA respectively. Appropriately defined F inverse and G inverse are injective. Such sequences indeed partition A disjoint union B. Okay, so here it's maybe I will say that prove this as homework. You will understand the use of equivalence relations better. Now again, same thing. If C0, C1 and C2 are three elements which lie, such that C0 and C1 lie in the same sequence and C1 and C2 lie in the same sequence, then looking at their position, C0 can be here, C1 can be here, C2 can be here. Then from C0 you can go to C2. Yeah, if C2 is here, then you can again go to C0, come back and then C2. So basically two elements are related if they can be obtained from each other by application of F's, G's, F inverse and G inverses. Yeah, and because all of them are injective, you can always cancel out the things which are common on both sides and continue doing this process. So this is a perfect partition. Now that it is a partition, the next defined function is actually well defined. Yeah, this is a function. Define h from A to B as little a maps to, okay, so G inverse A if A is in a B stopper sequence. And FA otherwise. Okay, we are making a choice over here. For all B stopper sequences, what happens? The first element is in B. So let us say this one. Yeah, we are in a B stopper sequence. So therefore, what could be the bijection? If my sequence starts here, the bijection is only possible if I pull this element back here, then here, then here. And because it's infinite, it won't matter. It will always be defined. Whereas for any other possibility, if it is two-sided infinite, so well, okay, let me give you some new form. So it's like and I have another color. Okay, so if I'm starting, this is the endpoint, then what function should I choose? Like if this sequence stops, then to establish a perfect bijection between the elements of this sequence, I must choose black color. Correct? Black color is a bijection. Blue color is not a bijection because it leaves out this particular element. And if it is two-sided infinite, then it doesn't matter what we choose. Yeah, black or blue, both of them are perfect bijections between elements of this sequence, which lie in A and B. So that's precisely what we have done. So A maps to G inverse A if A is in a B stopper sequence, and otherwise just f of A. Okay. Now whatever function we have defined, we have to show that it is bijective. So first we have to show it is injective. So let us do that. Oh, let's do something here. So H is injective. So suppose A1 and A2 belong to A and H of A1 is equal to H of A2. So now what can happen? You tell me, what can happen about A1 and A2? Can A1 be in a B stopper sequence and A2 not be in a B stopper sequence? Why?
Because either both will be there or not. Because if definition is fixed of f of a, then both are not in B stopper. But if the definition is of G must be, then both are in B stopper.
Yes, so yeah, first note that correct? So h of a1 and h of a2 are the same elements, yeah, that's important. Since h of a1 is equal to h of a2, both a1 and a2, sorry, I should say either both a1 and a2 are in a B stopper sequence, or both a1 and a2 are not in a B stopper sequence. Okay. So if they are both in a B stopper sequence, then what can we use to prove injectivity? So let me call this case 1 and this is case 2. So in case 1, h of a1, what will be h of a1 if they are in a B stopper sequence? So G inverse a1 is equal to h of a1 is equal to h of a2 is equal to G inverse a2, and this implies a1 is equal to a2 by injectivity of G inverse. And in case 2, what will happen? We'll always have f, yeah, f of a1. This is our definition, that h equals f in this case is equal to f of a2, and this implies a1 equal to a2 by injectivity of f. Okay, so injectivity is proven. Now h is surjective. This is also easy. Let B be in B. Yeah, we have to talk about B. What can happen with B? Either B lies in a B stopper sequence or it doesn't lie in a B stopper sequence. If B lies in a B stopper sequence, it lies in a unique sequence. Yeah, that's important. We are using it everywhere. If B lies in a B stopper sequence, then what can we say? Whose image is this B? Obviously, G of G inverse of GB is equal to B. Yeah. So G inverse of GB is equal to B, and then what can you say? We are in a B stopper sequence. So if B belongs to B stopper sequence, then GB also belongs to B stopper sequence. Therefore, H of GB, yes. So yeah, since B is in B stopper, GB also lies in a B stopper. And hence H of GB is equal to G inverse of GB is equal to B. Correct? And on the other hand, if B doesn't lie in a B stopper sequence, in a B stopper sequence. So the only elements, can you notice that the only elements which do not lie in B stoppers, which lie in B stopper sequences and which are at the beginning, are the ones which are not in the image of F. Let me go here. Yeah, if the sequence stops here, then this element is not in the image of F. And these are the only elements which are not in the image of F. Correct? So therefore, if B doesn't lie in a B stopper sequence, then F inverse of B exists, and H of F inverse of B will be defined as F of F inverse of B, and that will be equal to B, and this completes the proof. So we have shown that H is both injective and surjective. Any questions about this? Yes.
I didn't understand how that proves surjective.
Which part?
The last line.
Last two lines. This one.
No, so after H is surjective.
Okay. So we are starting with an element of B. We are calling it little b. Now B can lie in one of the three possibilities of sequences. Yeah, either it is in B stopper, or it is in doubly infinite, or it is in A stopper. If it lies in a B stopper sequence, then what does that mean? What can you say? That GB will always exist. Yeah, no matter where we are, GB always exists. But because B lies in the B stopper and GB is immediately the next element, so GB will also lie in a B stopper. So by definition of H of GB is G inverse of GB, which is B. So we have shown.
So how does that prove?
How does that prove what? Because see, this is the element whose image under H is B. Yeah, so therefore B lies in the image of H. Similarly, in the other case, we will consider F inverse of B. F inverse of B is the element which always exists, we argued that, and H of F inverse of B is actually F of F inverse of B, which is equal to B. Is that okay? And no? What's the problem? Okay? Okay. You are doing this, you are not this. Okay, any other questions? Yes. And what does it mean? These two lines? Okay. So if B doesn't lie in a B stopper sequence, then the sequence can be continued backwards at least one step, at least by one step. Yeah, either it could be doubly infinite, or it could be an A stopper, but we can go one step back. So what is the meaning of going one step back from B? It has to be F inverse. So F inverse of B exists, and therefore H of F inverse of B is equal to, right. Okay, now I understand when you look at this proof for the first time, it's quite confusing. I'm just going to erase this. But it is it will be clear when we look at this particular example. Okay, so let A be equal to the interval minus 1 1. Let me and B to be interval minus 1 1 in real numbers. Yeah, we are writing intervals in real numbers. Can you give me some injective functions from A to B and B to A? So F, let us write these things down, A and B. Give me some function from A to B.
X by 2.
Yeah, x by 2. So x mapping to x by 2 is a function from A to B. And what about the other direction? X mapping to x. Yeah, so these two are our functions. Yeah, let us call this f. Yeah, the upper one is f and the lower one is g. Okay, now what do we have to do? We have to create such sequences. Now, of course, these are not disjoint. Yeah, these sets are not disjoint, but we can make them disjoint by, let's say, embedding inside R square. Yeah, I mean, we have this plane and we are writing A over here and maybe B is written over here. Yeah, that's okay. Yeah, this is our A, this is our B. Now, whenever you embed B inside A, yeah, I mean it's just the identity map. What is left out? What is left out is really important. Huh? No, 0 is not left out. G is identity, yeah, whenever it is defined. So -1 and +1 are the only two elements which are left out. And whenever you map A inside B, you are actually reducing quite a lot. Yeah, you are only taking half of the interval, and then again when you iterate this process again it becomes half and half and half, and eventually it will vanish. But we don't care about the eventual behavior. Now you want to define a function from A to B which is bijection. Yeah, so want h from A to B which is a bijection. So if you follow the proof of this theorem, CSB theorem, yeah, there will be one question of this type in your tutorial sheet also, like follow the proof and obtain a bijection. What we will do is very simple actually. So we are going to map A to A by 2 or A, depending on two choices. If A is equal to plus or minus 1 over 2 to the power k for some k in natural numbers and otherwise. You follow the proof and you will get this function. Okay, what's happening? We are considering this A stopper and B stopper sequences. So for A, if we are at these 2 points, yeah, these 2 points are problematic, but their images are these ones, which you again embed over here. Then their images will be these one, which you again embed over here. So basically you are getting -1, -half, -1/4 and that decreasing sequence. And from here also you are getting 1, 1/2, 1/4 and that decreasing sequence. So you map every element in that sequence to the next element. And if an element doesn't lie in this sequence, then you simply keep it as it is. This is definitely going to define a bijection, and this is also based on the fact that there is a shift operator on natural numbers. Yeah, 0 mapping to 1, 1 mapping to 2, 2 mapping to 3. Yeah, n mapping to n+1 is a shift operator that is injective, and we precisely need that because these two elements are not present in B. So you simply follow your proof and you will get this. This you could have guessed anyway. Yeah, in general, maybe in your calculus course, yeah, if somebody asked you, are these two sets in bijection, you would have done the same thing. You could have chosen one sequence which contains -1 and 1 and any other and continue it indefinitely inside the interval -1 and 1, and then you just shift that sequence. Yeah, these two elements should not lie in the image. Shift the sequence and then you will get the image. This is our common thought process also. The proof actually generalizes this. Yeah, our idea. Can you please wake him up? You should also wake up. Yeah, there is no fan here, just air conditioning, so, and my voice is like a lullaby, right? Okay. So, any further questions about this? This you have to do it by hand, okay? Unless and until you actually work with this proof. So I am going to give you one more question for some two-dimensional subsets of real numbers, and then you have to follow this idea and see what really is happening. Yes?
How did you find the B stopper here? Like,
Well, I did not. I am just giving you that this will be the answer. Yeah, B stopper and A stopper you can always find. Yeah, I mean you start with a sequence. If I start with 1, yeah, if I start with 1, then what will be the, will the inverse image exist over here under G? No, it doesn't. So it's an A stopper. Okay, so maybe I am not using this particular definition. I am using F inverse of A if A is an A stopper and the others thing. Yeah, so you can always make choice whether you want to do it for B stopper or A stopper. Yeah, because for doubly infinite, see, for A stopper it must be F of A. For B stopper it must be G inverse of A. But for doubly infinite you have a choice. It can either be F of A or G inverse of A. Maybe I made a different choice in this example. If you actually follow the proof, maybe you will get slightly different function, but it's not going to matter. Yeah, that will still be a bijection. 0 will always map to 0. Yeah, but this is a very powerful tool. Cantor-Schroder-Bernstein theorem is a very powerful tool for proving that two sets are actually in bijection with each other, because generally finding explicit bijections is really hard. So let us go to another proof of the CSB theorem. So let me state the problem first. Yeah, so suppose phi is a monotone map from power set of x to power set of x where x is any set. So it's a monotone map, which means it preserves inclusions, containments. So whenever A is a subset of B, yeah, and both of them are subsets of X, then phi A is also a subset of phi B. That's a monotone map. Yes, you understand definition of monotone? It is inclusion preserving. Then actually this map has a fixed point, which means there exists some f which is a subset of X such that phi of f is equal to f. More generally, this is known as the Naster-Tarski theorem. Yeah, I have also written the name.
what is X here?
X is any set. Suppose X is a set and phi is a monotone function. Yeah, consider, I am just going to call it Y. Let Y be the family of all those subsets, B subset of X, such that B is contained inside phi B. Yeah, I mean B and phi B, they can be totally unrelated, right? B is a subset of X, phi B is a subset of X, and you have no control over what could happen. Understood this? But we are simply collecting these things. Now this collection may be empty, it may not be empty, that we don't care. Right? We just need this collection, and as both of them said, yeah, let C be the union of Y. All of you remember this notation, union of Y? What does it mean?
Union of every element.
Union of all the elements of Y. Yeah. So let C be union of Y, and we will claim that that C is equal to phi C. Okay, what is the first step of the proof? Whenever you want to show that two sets are equal, what do you show?
C is a subset of phi C.
C is a subset of phi C and phi C is a subset of C. Okay, so first part, yeah, so we'll show that C is a subset of phi C. Okay, how to go about that?
Show that union of phi belongs to Y and then.
Right. So let us do it element wise. Yeah. So let C belong to C. Then what will happen with C? Where does it belong?
In one of the element of Y.
Yes. Then C belongs to some B. For some B in Y. But then B is a subset of phi B, correct? So therefore C belongs to phi B, correct? C belongs to B, so it belongs to the left hand side, so it belongs to the right hand side, so C belongs to phi B. Moreover, B is a subset of C, correct? Because C is the union of all the elements of Y and B is just one element of Y, and therefore by monotonicity what can we say? Phi of B? Phi of B is a subset of phi of C. So therefore we have shown that C belongs to, little c belongs to phi of C. So we have completed the proof that capital C is a subset of phi of C. Okay, what is the second part? We need to show that phi of C is a subset of C. But what is the meaning of being a subset of C?
Every element of this is there in the other.
Yes, every element is there, but what is C? Look at C. C is the union of all Y's.
It belongs to Y.
It belongs to Y, yes. It will be enough to show that phi of C belongs to Y. Yeah? So I am saying enough to show that phi of C belongs to Y, because Y already, so C already contains union of all the elements of Y. Okay, so this is enough. How will we show this
Use
now?
one and take use that C is subset of phi of C.
Very good. So since C is a subset of phi of C, yeah, we have phi of C is a subset of phi of C by monotonicity. What does that show?
Phi of C belongs to Y.
Therefore phi of C belongs to Y, because that's precisely the definition. Right, so therefore phi of C belongs to Y, and we have completed the proof.
So how did you get the last step? Phi of C belongs to Y.
What is the condition? So B belongs to Y if and only if B is a subset of phi B. So phi of C is a subset of phi of C. So done? Any questions? So we have shown both the sides. So what is the fixed point?
Union of Y.
Union of Y or C itself. Yeah. You can do an alternate proof by considering the set of all those B's is subset of X such that B contains phi B, and then at that time instead of taking unions you take intersection. It will be a dual proof. Okay, any questions? Okay, let's complete the next proof then. suppose f and g are injective functions, okay, from x to y and y to x respectively. Yeah, this is the hypothesis of Cantor-Schroder-Bernstein theorem. We are trying to prove that. Then you define this map psi by this formula, psi of A is equal to x minus g of y minus f of A. You understand this definition? F of A is the image of this, then y minus f of A. So let us draw some pictures here. So suppose this is my x, this is my y, then this is my A. So what we are doing, we are mapping A to f of A. Yeah, A maps to f of A, then you consider this region y minus f of A, and then you take its image. Okay. Can you argue that this is a monotone map?
Yes.
It's easy, yeah? It is easy to show. Yeah, then this is monotone. So easy. If you cannot manipulate this much, then like manipulate sets, then there is something wrong. Yeah, you should know how to do this, that this is monotone. Then how do we define the function h that we need from between x and y, which is a bijective function?
So we use
f of x, like if x belongs to the fixed
One
point.
h.
Yeah.
So now define h from x to y. Where should little x go?
Do f of x if x belongs to the fixed point, or g inverse of x if x does not.
Okay. So I will say let f be a fixed point. A fixed point, okay, there may be multiple. We are just saying that there is at least one. Let f be a fixed point of psi. So x mapping to, yes, where should I send it to? F of x if x belongs to? Very good. And otherwise? G inverse of x if x doesn't belong to f. Why is this function bijective? Okay, so first of all, since f is a fixed point, since f is equal to psi of f, we have x minus g of y minus little f of capital F is equal to f. In other words, yes, take complements of both sides in x. Yeah, we are using the word complement here. In other words, x minus f is equal to g of y minus f of f. Well, this precisely shows, since g is injective, on x minus f, g inverse will serve as the required function, and since f is injective, f will serve as little f will serve as the function on capital F. The rest is simple verification. Yeah, so just being a fixed point is enough. So in the proof of Cantor-Schroder-Bernstein theorem that we covered in the class, we explicitly construct this fixed point. How? I will leave it to you. Yeah, for every function we explicitly construct this, for every pair of functions. Because I am giving you ready-made solutions, so you should at least try to see how this proof and that proof interact. There is one more start problem at the end, yeah, which says that read one more proof. Yeah, some of you actually came to me and showed me another proof of the CSB theorem. So there are multiple proofs, and you should familiarize yourself with all those proofs. Yeah, at least one more. This is the second one, then there will be a third one. So everybody should know at least 3 proofs of this theorem. Any questions about this? Okay, in that case, let me just pose this question to you. So R 0 1 and 0 1 square, I mean 0 1 cross 0 1 in bijection with each other. Are these two in bijection? One is simply an interval, bounded interval in real numbers, and another one is a filled up square in real numbers. Are these two in bijection with each other? Clearly, the interval can be embedded as a side of the square, but what about the others? We will actually prove that this is possible. That the square and the interval have the same cardinality. They are equinumerous. There is something called a space filling curve. So you start building that curve as a limit of some curves, and it will fill up the entire space, entire square. Right? Okay. So we will do this slowly, and all of you should revise a bit about equivalence relations. We know equivalence relation. We covered the definition of equivalence relations and partitions, but revise that. In the next class, we'll begin by defining integers, rational numbers and real numbers using equivalence relations. Because Kronecker said that natural numbers are God-given and everything else is a human creation. So we'll create them and then we'll start using them. Let's stop.